Well, here we go. Let's pray, and then we'll get started. Heavenly Father, thank you for today. Thank you for this time that we have to study matter, and as we finish up Hess's law and start to look at just really the wonders of creation, how things move at this level that we can't even hardly imagine, and how things move and interact at levels that we can, and how you're just completely in control of it all, and how there's just such great order to the universe. It looks like chaos, it looks random, but everything is just so designed. Father, I pray that we would walk away today with some semblance of that in our minds, and to appreciate your wisdom. We pray these things in Jesus' name. All right. Well, let's get started. Okay. So last time we did, I think we finished up with a problem where we used Hess's law. So what it took to make a series of different steps, and we used the enthalpy of those different steps to determine the enthalpy of a much bigger step. So basically what I'm saying there is, when you have a reaction that's complicated or dangerous, or you can't actually get at the things to do it, you don't have to do it to know the amount of energy that it's either going to release or absorb. You can use energy from known reactions in some kind of a table or whatever, and you can calculate it that way. So we're going to follow up the one we did. We had one more, I guess I skipped it. I realized it this morning when I was looking through what to teach today. And so it's kind of the follow-up to that, so let's do it before we do the big hard one. So, it says here, aluminum chloride can be formed from its elements, and so to do that you go simply 2 of solid aluminum plus 3 moles of chlorine gas, and they will combine to form 2 moles of aluminum chloride solid. We'd like to find out what the enthalpy is for this. Okay? We are given 3 things. Excuse me, we're given 4 things. There are 4 steps that we're given here. The first one is this, and I would write these down if I were you, okay? We're given HCl gas, converts to HC. Actually, let me put this in the middle. It's going to be helpful to do it this way. When you see me do something like this, where I'm intentionally putting something in a certain spot, pay attention to that. It might be just that I'm a nut, or I'm particular about something, but it might be that it's helpful. And so it might help you to do something similar. I think this is something that's helpful. It definitely helps me to keep organized. So HCl gas becoming HCl aqueous. So basically the dissolving of hydrochloric gas into water to become hydrochloric acid. That should say aqueous, not solid. Sorry about that. Okay, and this has a delta H of negative 74.8 kilojoules, right? So it's exothermic. Our next step is hydrogen gas combining with chlorine gas to form 2 moles of solid HCl. I say solid. I don't mean solid, I mean gaseous, sorry. And the delta H on this is also exothermic. It is negative 185 kilojoules. Our third step in this reaction is aluminum chloride aqueous converting to aluminum chloride solid. Delta H here is positive 323 kilojoules. Then our last one, we're going to combine 2 aluminum solid plus 6 HCl aqueous. Form 2 aluminum chlorides and 3 hydrogen gas, molecular gas. And our delta H here is negative, it's exothermic 1049 kilojoules. Okay. So I'm going to step away while you get that written down. So as we look at this, let's focus on our first reactant, right? I need 2 aluminum solids, right? Where will I find that? Call this, for our purposes, let's call this A, B, C, and D. Which one has my solid aluminum?
D.
D. I need 2 moles of it. How many do I have? 2. So this one looks to be okay. I probably don't need to do anything to this one to balance this all out, right? I need 3 chlorine, diatomic chlorine gases. So I need to find diatomic chlorine gas. Where do I find that? Oh. Not that you can find, there needs to be a 2 right here, I'm sorry. There's a subscript of a 2 on this chlorine that I left off. Which also tells you where it's at, right? So it's going to be B, my chlorine gas. I need 3 of them, so what do I need to do here? Multiply everything by 3. Now when I do that, this is, I'm gonna do it in a different color so that you can see, okay? So I'm gonna get 3 of these, I'm gonna get 3 of these, I'm gonna get 6 of these. But I also have to come over here and I have to multiply this by 3. Okay? Alright, now I need 2 of these aluminum trichlorides. So where will I find that at? AlCl3. And I need it to be solid, by the way.
C.
It's going to be in C. What do I need to do to this, to line C?
Multiply by 2.
Multiply everything by 2, right? So I get 2 of these, 2 of these, I need to do 2 of these. Okay? That leaves me with line A. Line A is going from HCl gas to HCl aqueous, which means I obviously going to be working, and I need, actually neither one, right? We know this will cancel out, but it's an important step in this. So I need to find my HCl I've got it here, aqueous, right? How many of these do I have?
6.
6. So I need to multiply this by 6. The only other question here is, do I need to reverse signs on anything? I want solid aluminum on the left. I've got it. I want chlorine gas on the left. And do I have it? I have it. No, that's not it. Where is it? Right here. I've got it. Okay. And I need solid AlCl3 on the right. And I've got it. And everything's in the right number. So this should balance. If I now just go through and take out the things that on both sides of this equation, right? I've got, let's do it this way. HCl gas is here on the left. I'm looking for HCl gas on the right. Right, so I know those two are going to cross out. HCl aqueous is on the right, so I'm looking for it on the left. So those two are going to cancel out. Okay. H2 gas on the left. I got 3 of them, so I'm looking for it on the right. Those two cancel out. I want my 3 chlorine gases on the left. They're there, so that's good. AlCl3 aqueous on the left. I don't want that. I've got it over here on the right. That's perfect. That's going to cancel out. AlCl3 solid is on the right. That's what I want. And 2 aluminums on the left. That's what I want. So now when I bring all this down, I get 2 Al solid plus 3 Cl2 gas, yielding 2 AlCl3 solid. That's what I want. Now the only thing left to do is the summation of all this, right? 6 times negative 74.8 plus 3 times negative 185 plus 2 times 323 plus negative 1049. So if you guys would humor me and do that math. Oh, let me get some calculators. Cheers.
Yeah.
Mazel tov.
Well, you said you did. You said I did.
Okay. What you got?
Negative 1,406.8.
Negative 1,000 what?
406.
406. 1,406 point something or
0.8.
like 8 kilojoules. We get that same number?
Yeah.
Yeah. Which would round it to 1,407, which is what they have. That's perfect. Perfect, perfect. Good. Okay. You're going to go watch that video from last class to catch up. Good. Good deal. Okay, well, let's do the next problem. This is the last one we'll do. We're going to skip it. It's not that important, truly. I'm not giving it to you on the test anyway, so there we go. Let's dive in to Let's dive into to a video. That's not the one I want. I want this one. Do one more thing, sorry. Here's the screen. You guys are seeing what I'm seeing. So here's the deal. As we move forward, we're going to move a little away from this branch of chemistry. And we're going to move more into how matter behaves at an atomic level. Concepts like electronegativity, the charge in the nucleus, the charge on a proton, charge on a neutron, charge on an electron. You understand that the electrons move around in these things that we call orbitals or shells or clouds, and the lowest energy, electrons always want to be in their lowest energy level. In fact, everything in the universe wants to be at its lowest energy level. That's where it's the most stable. That's just part of thermodynamics and kinetics, that everything is always moving from high to low. Everything going at high to low concentration, high to low energy. You know that the first orbital holds 2. Once it has 2, it's full, and it goes out to the next one. The next one holds 8. But eventually we're going to get to where the rules get kind of crazy. How do you know where an electron's at? And can you do calculations with it? And why is it that that atoms emit light? And how is it that atoms absorb light? You know, I'm teaching chemistry, obviously I'm teaching chemistry. I'm teaching astronomy also this year, right? So in a second semester astronomy, which is the one I'm teaching, is all about stars. Well, what's the number one you think of when you think of a star? Light. Where does the light from a star come from? It comes from the atoms. Literally, it comes from atoms, right? Atoms being formed. Atoms, as electrons are moving around, and they're coming back down, they're coming back out. Light is, in stars, light is created out of matter. Literally. Have you ever heard of a positron? So, you know what an electron is, right? What's the charge? Negative. What's the size? I mean, it's tiny, right? We'll have a problem with it maybe later today. We'll see how far we get. But it's tiny. Well, and it moves fast or slow? Fast. Not as fast as light, but super fast. Well, a positron is the same, except it has a positive charge. Well, here's the thing. So positron is what's called antimatter. So there's matter and there's antimatter. So whenever a positron is formed, what charge does it have? Positive. Well, if it's around a bunch of matter, and matter consists of electrons, then those have opposite charges and opposites attract. And so a positron and electron, when they're created in nuclear fusion inside of stars, they collide into each other almost instantly because they're like magnets, and then it produces a muon, which is a whole other thing, and it produces gamma rays, and so it literally produces light. But there's all kinds of other light being emitted by stars. As the star's hot, electrons are doing their thing, and light's being emitted. But it's coming primarily from the activity of electrons. And so think of something like hydrogen, okay? If I were to draw hydrogen here, generally we represent it as having just one proton, right? And how many electrons? One, right? Generally one proton, one electron, if it's neutral. So that electron's going around at its lowest energy level. What would it take for it to go to a higher energy level? For this electron to suddenly go into a higher energy level, what's it going to take? Let me back this up. Let me ask you a question. If you were in a car and you were in an open field or something like that, and you just barely pressed the gas and you had that wheel cranked all the way hard left, right? Then your car would go like this, wouldn't it? I mean, it would just go around and around and around, right? What if you stepped on the gas? Would you still be in that tight circle? You couldn't stay in that tight circle. If you increase your gas, you're going to increase your velocity, your energy, right? And so you're going to start to go out here, right? And if I add more gas, more energy, then I'm going to start to go out here. And if I did it again, I'd start to go out here, right? Every time I add energy, I get further, the diameter of my circle gets further and further away. That makes sense, doesn't it? Yeah? And if I took my foot off the pedal but kept my steering wheel still as tight as I could, then this circle will start to come back down, won't it? It just makes sense. If I have more energy, where's that energy? That energy's gotta go somewhere. It's gonna force me out further. So how does an electron go from its lowest energy level to a higher energy level? In fact, it's in the name, right? It's energy. It's got to absorb energy. And how does an electron come down from an outer level to an inner level? It has to release energy. The release of energy from an electron moving from a higher energy level to a lower energy level is in the form of light. It emits light. It radiates light at very specific wavelengths. And if I want to excite one from here to here, I can do it by having it absorb light. You experience this all the time. You ever use a microwave? What are microwaves? They're just light. Just light. They're not even particularly high energy. Like an individual microwave is lower energy light than, I'm sorry, I said that backwards. They're higher energy light than our visible light, but they're not. It's that we're bombarding the food with them, and it's hitting particularly water molecules inside the food, and that energy is being transmitted and heating the food up. Well, where do the microwaves come from? They come from atoms that are getting excited by electricity, and then when the electrons fall back down, they emit light that goes into your food. Light that you and I can't see, it's not the visible spectrum. But you deal with this is how your phones work. It's how everything works, whether you can see the light or not. This is how light works. So what are the rules for this? What's happening? What is light? Like literally, what is the nature of the light? What's the relationship between light and electrons and all other types of matter? That's what we want to see today, okay? So, pay attention.
Is to understand the events in science which forced us to adopting these somewhat counterintuitive conclusions. Where it all starts is potentially with a man named René Descartes, who's a French polymath who does geometry and physics and philosophy and all sorts of things. And he developed a corpuscular theory of light. A corpuscle is a particle. So he's saying that light is a particle which travels in straight paths unless something causes it to be perturbed from that path. So it's like a billiard ball. It can bounce off of surfaces, but otherwise it's always traveling in a straight line.
You're familiar with this. If I had a mirror there at the back of the room, and I took a laser and I shined it on the mirror, you know, if I had the mirror dead center and I shine the mirror or the light right here, right at the mirror, where's the beam going to go? Nah. It's going to go equal and opposite. So if I shoot it at a 45-degree angle this way, it's going to go 45 degrees that way, right? That's the same thing that a ball would do. My little boy was asking me about how mirrors work the other day. And so I grabbed a little tennis ball and I said, well, I want you to sit over, you know, I said, I'm going to throw it off the wall. Where's it going to go? And he gave the same answer. It should come right back to you. I said, okay, well, let's see. And, of course, it goes equal and opposite. I say that to say that a ball is like a particle. It's like a thing of mass. And so you expect, the rules say for every action there's an equal and opposite reaction. Whatever angle I throw it at, it's going to come off the opposite with the same energy, assuming no loss to heat or friction or whatever else. We deal with that with light all the time. It's how a rear view mirror works. It's how side view mirrors work. It's how all these things work. This is very logical, his explanation of it. We see this, but it's not sufficient. I won't say it's inaccurate. I will say it's insufficient.
So, for example, your candle is going to be emanating these particles which travel in straight lines in all directions and cause the illumination of the surroundings. Now, in 1690, Christian Huygens develops a competing theory. It's the wave theory of light, which says that light radiates in surroundings like ripples in a pond. So you can imagine here, if we throw a pebble into a pond, the ripples migrate. Well, he says that light's the same thing. So if you have a candle here, then we have waves of light radiate out into the surrounding room.
Again, we see this. This is simple. If you were think about like being at a dock or something on a lake, maybe, and I got a dock here, and I obviously don't own a lake house, but if I did, or if I were visiting somebody who did, and there were a bunch of docks, right? Here's shore, okay, and I did just the world's biggest cannonball right here. What's going to happen? Waves are going to form, right? In which direction? All directions, right? So they'll go like this. And now what happens from here? They go out, right? But what happens with the next one? Here's my question. Sorry, you're answering a different question maybe than what I'm thinking of. Does it just keep going like this? No, it continues to expand. And if you get far enough away, the effect of having most of this absorbed by these docks you would never know, right? Because it keeps radiating out, right? Propagating is really the word. Light's the same way. So if we turned all the lights off and I had an incredibly bright source of light and a narrow door, and you could see that light coming through at the start of the door, this part would be in darkness, right? And this part would be in darkness. But as you got over here, it would not, right? Because it's going to radiate out. So on the one hand, you've got light behaving as a particle, right? It bounces. On the other hand, you've got it acting as a wave. Particles and waves don't seem to be the same thing. They don't seem to behave the same way. So which one is it? This is...
Now if we have some aperture, so our candle, or in this case a match, is throwing out its light as it goes through a hole, then it will start radiating again anew from that hole. So then we'll have waves propagating like that's the origin point. Now the question then is, which of these is correct? The particle picture or the wave picture? Well, the problem is that they give very, very similar conclusions as far as their physical predictions go. Now, Isaac Newton, who's an incredible bigwig in science, throws his weight behind the particle theory, and so everyone sort of throws Christian Huygens to the wolves and says, if Isaac Newton is backing the particle theory, it must be correct. But there's still no way to tell definitively who's right and who's wrong. The resolution comes in 1803 due to the English physicist Thomas Young. he develops a double slit experiment which passes light through two slits and analyzes the result to determine whether or not it's truly a particle or truly a wave. And this is possibly the most important experiment that has ever been performed in all of science. And according to Richard Feynman, the renowned physicist, if you truly understand this double slit experiment, then you understand quantum theory. Now before I show you the double slit experiment, let me first show you a single slit experiment. So for a single slit experiment, we have a box with a single slit on it, and we're going to fire our light through. And let's say the light's a particle. Well, so provided we have a very small slit here, about an order of the size of the particle, then in the main, the light will come through and hit the center of the slit. But because of the edges of the slit, they're going to diffract out a little bit as well. And so we will get some fading intensity over here in our detector. This picture you can imagine is a photographic plate, which is picking up the intensity of the light as it falls on it. And if we were to plot that intensity, then we would get a curve kind of like this, where we have a very intense region at the center and then tapering off at the edges. Let's say instead that light is a wave. Well, now again, the main intensity of the wave is going to fall on the center of our detector, and it's going to taper off on the edges. So we'll actually get an identical picture, and if we were to plot it, we would get the same result. So in this case, we can't actually distinguish between light behaving as a particle or light behaving as a wave. Now let's say we have two slits. Our particle light would go through one slit and diffract a little bit and give us an interference pattern like before. We would do the same thing with the second slit. And so what we would get is just that same pattern twice. We would have two peaks in our intensity plot. Well, let's consider if light is a wave. If light is a wave, then when it comes through these apertures, remember those act as new origin points for more waves. Well, now we get an origin of waves here and an origin of waves here, and they eventually overlap. And where they overlap, they create an interference pattern. Peaks add together to give bigger peaks. Where peaks and troughs meet, however, they cancel out to give null regions. And so you get something that looks like this, where sometimes the waves subtract, and there's nothing there. Sometimes they add together, and we get regions of high intensity. And our plot would look like this. We should recognize as an interference pattern. So in this case, the results are very different. And by performing this experiment, we should be able to definitively discern whether light is a particle or light is a wave. Well, we performed this experiment, and this is the result. It's done with some laser light in this case. So we definitely do, in the double slit case, get these fringes which indicate an interference pattern. So this is a conclusive result that light is a wave. Only waves interacting can generate an interference pattern. Well, great. So we've
People pool. And you get two people and they're pushing water towards each other. They're taking their hands and they're creating a wave, right? If these waves hit at the exact same time, what's going to happen to that water? So the water's traveling like this, right? The water's going like that. If these waves hit the exact same time, what's going to happen?
they cancel out.
Nah, if they hit just right, I'm sorry. I should have. It depends on whether they hit in phase or out of phase, right? If they hit perfectly in phase, then when they hit, they will amplify each other. If I hit two peaks at the same time, I'm going to get a double peak, right? But if I hit two troughs at the same time, I should get like a double trough, right? But if I hit a peak and a trough at the same time, they should cancel. You've experienced this in your life on a trampoline, right? you're jumping on a trampoline and somebody else gets in and they're trying to double bounce you, right? What are they trying to do? They've got your wave running through it and they're trying to add their wave to it, and then you go, woo, right? But sometimes you get dead-legged on it and your wave hits out of sync with their wave and you fall to the trampoline and feel like you broke an ACL or something. You tore it, right? That's what he's talking about interference patterns, right? So if they hit just right, you get amplification. If they hit just right the other way, then you get phase cancellation. Right? It also happens with sound. You ever been somewhere and you get like this out of the sound and it's not at a rave or something like that? Like, that's because the two sources are interfering with each other, and you get a when it's amplifying and you get a when it's canceling. Okay.
Figured out that light is a wave. We can use Newtonian mechanics to treat the behavior of the waves, and science is solved, and we can close our books and go home, right? Well, unfortunately, it's not true. In fact, in the late 19th century, we encounter a new problem, which is pretty severe, so severe that it is designated a catastrophe. It's called the ultraviolet catastrophe. Now, to understand the problem, whenever we have a warm object that's going to radiate energy at every wavelength. Now, according to this classical theory of waves, whenever these waves radiate, they're going to radiate at every wavelength with an equal energy, an average of 1/2 Boltzmann's constant times the temperature. And this is going to occur at every wavelength, every frequency, which means we're going to have infinity times this value for our total energy in our space, which is going to be infinite energy. So you can imagine we have our oven over here, and so we're going to be allowed any infinite number of wavelengths between one side of the oven and the other. Each of those will carry energy, adding up to an infinite amount, and as a result, our cookies are going to be incinerated along with the rest of the universe. That's a big problem and indicates something is fundamentally amiss with our picture of how light works or how energy works, or something is not right with our understanding of the universe, and very extremely so. Well, the solution comes in 1900 due to the German physicist Max Planck. And Planck proposes that light energy can only come in multiples of a specific quantum value. That's usually designated with an h, and h is equal to 6.626 times 10 to the negative 34 joule seconds. Now, why is this so? Planck doesn't really know, but he works out the formula. And so our frequency is always going to be some integer, some number of cycles per second, and we'll multiply that times is constant, and we're not going to be able to have anything in between. So we can't have half of an h, but we can have 1/8, or we can have 2 h's or 3 h's, etc. And that will give us the allowed energies of light. And the result, when you integrate that into the 19th or 20th century picture of statistical mechanics, is that now you get finite energy values in your oven, which is good. We know they have to be finite. Now note that there's another important relationship, that the frequency is equal to the speed of light divided by the wavelength. This V with kind of a tail in it, by the way, is the Greek letter nu, which we use to stand for frequency. And this is the Greek letter L, lambda, which we use for wavelength. And so we take the speed of light, we divide by the wavelength, that should give us the frequency. And so we can substitute this in for frequency in our E equals h nu expression. And so we can also write Planck's formula this way: E equals hc over lambda. And one or the other might be more convenient depending on whether we have a frequency or a wavelength. Now again, so we have this resolution to our infinite energies problem, but we have the question, why is it that light comes in multiples of these energy quanta? Now, Max Planck, he's come up with this equation, and he doesn't really have a reason for it, he just knows that it works. The hero who pulls this all together is none other than Albert Einstein. In 1905, he publishes 3 seminal papers. One is on Brownian motion, the erratic motion of pollen granules when suspended in water, which he explains as being due to the fluctuations of molecules impinging on the surface of the pollen grains in different ways and different sites. And that brings everyone in the world onto the same page that molecules and atoms really do exist. He also publishes a paper on special relativity, which connects matter and energy and allows for describing the behavior of physical systems at near light velocities. And he publishes one more paper on the photoelectric effect. The photoelectric effect, this is when you shine a light on metal and you generate a current. You free some electrons. This is how solar cells function.
Let's go back to the microwave thing. I'm not saying you should do this, I'm just saying I have done it. I used to do it whenever I taught photosynthesis, each year I would do this so the kids could understand how light and all these things work. So you take a microwave, and we know that we've got light coming in from the microwave, right? Doing its thing. And then I take kids, I didn't have to bring my own, kids always had them, they'd come in with them, these bags of chips with the little Mylar bags, they're like silver on the inside. Cheetos are always the ones that stick out in my mind. We take an empty one, okay, and we put it in the microwave. Well, that Mylar is metal. So you know, hey, don't put metal in the microwave, right? What happens if you put metal in the microwave? So what I'm doing in this case is I'm shooting light at metal. That's what Einstein's doing. He's shooting light at metal, and what happens is when it does that, the electrons in that metal take off. Moving electrons is called electricity, and you get this happening. And it would only last a second. You didn't have to leave that thing in there very long at all. And what was really cool is because you're adding all this energy and all this electricity, this bag that was this big would shrink down to like nothing. But you could still read Cheetos on it. It was super cool. And it did not destroy my microwave in all the years that I taught. It was always okay. There. So that's the photoelectric effect. We shoot photons, right? Light photons at a metal surface, and it emits electrons, electricity. That's what he's doing here, except on this genius level, and I'm just some idiot with a microwave. But
according to the classical theory, when you shine a light on a metal, the energy from the light is absorbed by the metal and ejects the electrons. And the number of electrons that are going to be given off is going to be proportional to how bright that light source is. And the less bright it is, then the longer it's going to take to give the metal sufficient energy to start kicking off these electrons. So that's the classical description. Now, unfortunately, experiments are not very cooperative with this theory. First of all, the metal only emits electrons if light is above a certain frequency. If it's below that frequency, you can shine light on it all day. It's never going to charge up the metal enough to give off those electrons. And furthermore, you actually don't need to charge the metal up at all. If you have the right frequency of light, you shine it on the metal, it will start emitting electrons instantly. No charge-up time, like the classical theory had predicted. So what's wrong here? Why is the classical theory failing so horribly at describing this effect? In his paper on the photoelectric effect, which by the way is the one for which he was awarded the Nobel Prize in 1921, Einstein proposes the following solution. He says that light is made up of particles, which he calls photons. Apparently that rolls off the tongue a little bit more than corpuscles, like Rene Descartes used. And these electrons are only going to be ejected if the energy of the photons is enough to dislodge them from their position. And so if you don't have a frequency that's high enough, that's going to give you a high enough energy, then irradiating the electrons never gives it what it needs to vamoose off the atom. And this is a little bit weird now. We have proof that photons are particles, but we also had proof from the double slit experiment that they're waves, that light is made up of waves. So Einstein proposes the concept of wave-particle duality, that sometimes light behaves as a particle, but sometimes it behaves as a wave. Now we know from our discussion of waves that really light is always a wave, but sometimes it's kind of a more wavy-like wave, and other times the wave can change shape so that it has more the sense of being a particle and having a particular position. But in all cases, the wave really is just different kinds of waves, particle-like waves and wave-like waves. So that's a little bit weird, light behaving as both a wave and a particle, but it actually gets even more bizarre. In 1909, the English physicist and mathematician Geoffrey Taylor asked the question, what happens if we fire a photon through the slits, one at a time? Well, so we send one photon through the slits, and it goes and is absorbed by our detector. Then we send another photon, and another photon, and another photon, and then we develop our photographic plates, and this is what we get. We get an interference pattern. Now, the only way we can have an interference pattern is if we had a wave interacting with a wave. So what that must mean is that our photon actually went through this slit and this slit, generating a new wave source from the bottom slits and a new wave source from the top slit. Those wave sources interacted with each other and gave us this interference distribution. But, if we keep in mind that light really is a wave, then maybe it's not that bizarre, because waves can definitely do that. Regardless of how much light we have, if light's always a wave, then it can always behave as a wave. But now something else that's pretty bizarre, if we actually check, because we're suspicious, does light really go through both slits at the same time? Maybe we'll put an observer at one slit and see if every time we fire this photon through, it goes through this slit as well as this other slit. Well, if we check, then we will no longer have an interference pattern. We'll have light go through this slit and build up particle-like distribution, or it can go through this slit and develop particle-like distribution. So now our photographic plate will look very differently just because we're checking which slit the photon goes through. So what's going on here? Well, if we leave the photon alone, then it's free to behave as a wave and interfere with itself and generate the wave pattern. However, if we observe it, then that interaction changes the shape of the wave to a more particle-like case where it has a definite position. So basically, we force its position to be at one slit or another by interacting with it, and now it goes through whichever slits it's at as a particle instead of going through both slits as a wave. Now, nothing really fancy happened. All that happened was that we altered the nature of the wave that was going through the slit. If light can have a dual persona, in which sometimes it behaves as a wave, but other times it behaves as a particle, then why can't other things also have this dual persona? Well, this is a question asked by French physicist Louis de Broglie in 1924. And he proposes that the electron can also have a wave identity in addition to its particle identity. And he also provides a formula in order to determine the wavelength of the particle in question. He says that the momentum of the particle, which is mass times velocity, is equal to Planck's constant divided by the wavelength of the particle. And this wavelength is now called the de Broglie wavelength. Well, this doesn't really go over very well. He submits this idea for publication and no one will publish it. They think it's absurd until he writes to Albert Einstein, who came up with the wave-particle duality idea. And Einstein thinks that this is a fantastic proposition, and he co-authors the paper with de Broglie. And then everyone has to publish it because now it has Einstein's name on it. All right, let's go ahead and figure out the Broglie wavelength of a piece of matter. In this case, we'll stick with an electron. We'll consider the electron which is bound to the proton in a hydrogen atom at room temperature. And this can be considered to have an average speed of 2,200 kilometers per second. And do we really have a speed when speed is distance divided by time and we don't have defined positions for the electron at any point? Not technically. So speed might mean something a little bit different here, but it's something that we can infer from the kinetic energy of the electron. It has the energy it needs to move at this velocity if freed from the proton that it's bound to. So we'll go ahead and say, yeah, this electron has a speed of 2,200 kilometers per second. Then what is the wavelength associated with this electron? We can use the Broglie equation, which relates the wavelength to the momentum. So we can solve the Broglie equation for lambda. Lambda is going to be equal to Planck's constant divided by the momentum. And remember, momentum is mass times velocity, which in this case, that's easier for us to figure out. We can look at the mass of the electron and we are already given its velocity. So now it's just a matter of plugging in the mass of an electron. We look it up. It's 9.109 times 10 to the negative 31 kilograms when it's at rest. And Planck's constant, 6.626 times 10 to the negative 34. We're going to want to use units that match the fact that we have mass and velocity. So we'll use the version where we have meters squared times kilograms per second.
Because a joule is actually equivalent to that.
Plug in
Meter squared kilogram per second.
equation for lambda. Lambda is equal to Planck's constant over the mass times the velocity. And just a last bit of tidying up. Since we're talking in meters and Planck's constant, we'll go ahead and convert this kilometers into meters here. So now this meters will cancel out one of these meters squared. Kilograms will cancel out kilograms. Per seconds will cancel out per seconds. And we'll get units of meters, which is what we were looking for. We're trying to find a wavelength. So we definitely want to get units of length. And it comes out to 3.3 times 10 to the negative 10 meters, or 3.3 angstroms. Now the diameter of a hydrogen atom is on order of about half an angstrom. So the wavelength of this electron is much larger than the hydrogen atom itself. In general, when the wavelength that you calculate is on order of the size of the system, or even within a few orders of magnitude of the size of the system, that means you're going to need to consider it as a quantum system and use quantum mechanics to come up with a reasonable solution. On the other hand, if the wavelength is extraordinarily small compared to the size of the system, then you can probably skate by doing classical mechanics. Now, for example, if you were to calculate your own de Broglie wavelength, you would find that it was fantastically small, and you would never, for example, be able to construct a double slit experiment in which you would actually be able to fit through the slits, which were constructed to be the same size as the de Broglie wavelength. So you don't have to model yourself as a quantum system to figure out the nature of your trip to the grocery store. But electrons, we just found out that the electron for a hydrogen atom has a wavelength several times larger than the atom itself. So definitely we have to treat that as a quantum object. And in fact, what if we were to subject electrons to the same kind of test that we've been considering on photons? Well, in 1961, Klaus Johnson has done this. He performs the low-intensity double slit experiment, where we're sending one particle at a time through the slits with electrons. And what he finds is that you do get an interference pattern, which means the electron is behaving as a wave, passing through both slits at the same time, and then its two wave aspects interfere with each other, and then we get this probability buildup, where we have high intensity regions and low intensity regions, confirming that it is in fact a wave. And since then, this kind of experiment has been done with atoms and then molecules. And at this point, we've done it with molecules which contain hundreds of atoms and gotten the same effect. Now, at some point, there's a cutoff where we're not going to be able to observe these quantum effects anymore. But we're still pushing the limits there. And it's kind of incredible that you can have these big molecules and they do the same weird things that the photons and electrons do. They have wave natures which can go through both slits at the same time, interact with each other, and generate an interference pattern.
So why did I make you watch that? Which either fascinated you or put you to sleep, or maybe a little bit of both. What do you need to take away from that? A little bit of time that we have left. Whether we're talking about light, whether we're talking about electrons, whenever we're talking about something incredibly small, you see it behaving both as a particle, right? So an identifiable thing that we can see, we can track, we can plot, but you can also observe it behaving as a wave, where it's propagating. It can be in two places at the same time. It can interfere with itself, and that's wild. And it has big ramifications within an atom. You get something like Heisenberg uncertainty principle. You just can't know everything. You can't know where an atom's or an electron's at and know its momentum at the same time. And if I know its momentum, I can't know where it's at. If I know where it's at, I can't know its momentum. I can't. Because there's something happening at an atomic level that we don't fully understand yet. With all that we've learned, with all we understand, we don't understand. And so even today, there's a search for a unifying theory of everything. We understand what happens at the big level, right? I mean, we can, think about this, we can launch a missile or a rocket or something, and if I know all the variables, I know exactly where that thing's going to be, right? I can't, if I knew the variables on an electron, I'll have no idea where it's at. If I know where it's at, I don't know where the other things are. How do these two things align? Well, we're not going to solve that. But it has a lot to do with what's happening at the atomic level. Okay.